King County, Washington State. Home to Seattle and Bellevue, hubs for the USA's booming tech industry. Where population is exploding and traffic is gridlocked. Engineer John Slavin lives and works in a city pushed to breaking point.
Seattle's experiencing some of its rapidest growth since the gold rush back in the 1800s. We've had more tower cranes in Seattle than any city in the country for a number of years running. With a lot of major corporations in Seattle, the traffic's getting worse, the need for transportation is increasing, and the need for choices are increasing.
The solution could be to link the cities by train. But in King County's unique environment, even railways face a problem.
One of the unique features of Seattle is its geographic terrain. There are a number of lakes that all restrict where and how you can place transportation services. And in particular, Lake Washington sits between downtown Seattle and Bellevue, both of which are high-tech areas that need to be connected.
In a landscape strewn with vast bodies of water, Lake Washington is the largest and deepest. Here, traditional bridges just aren't possible. When it comes to water, cars and trains are stopped in their tracks. Indigenous people used canoes to get around Lake Washington for thousands of years. 19th century settlers used ferries, bringing in so many boats that they became known as the Mosquito Fleet, clogging up the waterways. A more practical solution was required. But with almost 2.5 kilometers to cross and water and soft silt over 100 meters deep, neither a traditional bridge nor a tunnel could solve the problem. But engineers in Seattle have the answer. This once impassable lake has now been conquered by the incredible I-90 floating bridges. A concrete megastructure that actually sits on the surface of the water unsupported by columns.
There's a lot of engineering that went into this to make this all happen, and it's pretty cool to work on.
This project is incredibly unusual in that we're applying systems that has not been done by anybody else in the world ever before. The engineering behind this project is mind-blowing.
These extraordinary buoyant bridges are capable of carrying 142,000 cars a day. But now they're entering the next and most challenging phase of construction. Adding a state-of-the-art train line and creating the planet's only floating railway bridge.
What makes this project so exciting for me is nowhere else in the world has this ever been done. It's floating, it moves. We're essentially putting rail on a marine vessel. It's a very unique engineering achievement.
With a massive 324,000 tons of reinforced concrete, the twin floating bridges weigh more than 52,000 elephants. All that weight is floating on 38 monster pontoons, with nothing but 64 meters of water below the surface, crossing a span of nearly 2.5 kilometers and capable of supporting the weight of high-occupancy rush-hour traffic. The finishing touch will be a revolutionary railway line, a world first on a floating bridge.
Once this system is commissioned and in operation, this will be an engineering feat like no other.
But this ambitious project poses huge engineering challenges. How do you connect a railway from land onto a floating and so moving bridge?
If those rails were just attached on either side, that continuous connection would experience all those movements in one point and would probably snap the rail.
What happens when you introduce a high voltage current to a structure in water?
there is a risk of stray current escaping from the rails, which could get into the critical bridge structure.
And how do you make it strong enough to support 300-ton trains?
We can eccentrically load the bridge and potentially crack it. That would not be good.
But the biggest problem of all, how to keep the concrete superstructure afloat.
It is very important that if there's any water intrusion, that won't sink the whole bridge.
Engineer Jim Stonecipher knows all too well the daunting complications of building on this lake.
The lake is deep, and being in earthquake country, we need a good material to set our foundations in, and it's just not available on the bottom of Lake Washington. Before you can get to some good material, you have to go through silty sand, and so you might end up with a column that's 500 feet deep.
Even if engineers were to sink support columns through 65 meters of water, they would hit a soft lake bed made of silt and clay. Pillars would need to go through another 50 meters of sediment to reach a solid footing. Add the column length needed above the water, and all this makes for an incredibly expensive and unstable structure.
On the engineering side, it would be difficult to build a standard cable stay or other type of bridge in that area. It takes a unique kind of bridge span to span Lake Washington.
So the engineers' only option is to float the bridges. But how can they ensure the giant concrete structure doesn't sink? The answer lies with a pioneering innovation of the past. On the Caribbean island of Curacao, local engineer Albert Zweste is exploring how a clever piece of engineering could help the team at Lake Washington.
We are located here close to Panama, where they have the Panama Canal. So the island is strategically located for the shipping routes and for trade.
The island's main town, Willemstad, was a perfect port. But by the mid-1800s, the deep natural harbor was creating a problem.
The town is separated in two halves, but about 4,000 people per day needed to get across. And they did it in small boats. And you can imagine it was time-consuming and not efficient process.
But the channel is 150 meters wide and 15 meters deep, with a soft sandy seabed, making most bridges impossible to build, especially one that allows the passage of ships into the harbor.
Okay, here we have the two sides of the town. I'm going to show you now the options that we have to construct a bridge between them. The first one would be a beam bridge. It's a cheap and easy bridge to build. We can put it across and people can walk over to the other side of town. The only thing is, traffic could not go in and out. I have a boat here, needs to go to the harbor, cannot come in. Also, I need a lot of support and the sea bottom is soft, so we'll grab another one. The arch bridge solves the problem for vessels coming in, but only small vessels. An arch bridge would be expensive to create the arch and to make it high enough for larger vessels to come in. The bascule bridge is an option that gives us the possibility to open it and let traffic go in and outside the harbor. It doesn't need to be that high. So we can pull on this, open it up, and my vessel can go in or out. The problem with the bridge is, though, I need heavy foundations in a town that's already been built in a deep channel with soft foundations. So this bridge, although beautiful, is not an option for this site.
But when American ice merchant Leonard Burlington Smith sailed into Curacao in 1876, he had the answer.
So this is what Smith came up with. This is the Queen Emma Bridge, a wooden pontoon bridge with 17 pontoons stretching across this channel, the Anna Bay.
Affectionately known to the locals as the Swinging Old Lady, it's one of the oldest pontoon bridges in existence.
This bridge uses about 600 tons of wood, each pontoon 15 tons of steel. You see it moving? We are now completely floating on the water.
But the brilliant pontoon design not only allows for transit between each side, the floating bridge has another trick up its sleeve.
We've got a boat coming now, so we need to open the bridge all the way up to let this boat get out to sea.
The impressive 167-meter bridge span is hinged at one corner and swings open, allowing boats access to the harbour.
To be able to open the bridge, we have two motors, one in forward, one in reverse. Together they push and open the bridge. We get oil tankers, we get container vessels, we get cruise vessels come in here, all kinds of vessels. It was genius. It was a quick solution, an efficient solution, and a relatively cheap solution.
Smith's design was brilliant in its simplicity. Located just beneath the public concourse lies the vital components that will prove significant to the engineers of Seattle.
Okay, we're here on one of the pontoons. The pontoons are the most important feature of the bridge. All this weight is carried by the pontoons. No columns are needed to anchor this bridge into the sea bottom. Now you can see that the bridge has more than one pontoon. This is to displace the weight, of course, and the length of the bridge, but also the pontoons give us redundancy. If one gets damaged, it can be removed and can be replaced by another. When it's removed, the other pontoons will carry the weight.
Pontoon bridges may have been around for millennia, but few have lasted quite like the swinging old lady.
Walking on this bridge, it's an amazing feeling, and it gives me goosebumps every time that I walk over it and every time that I see it open.
On Lake Washington, engineers have taken the idea of the pontoon bridge and supersized it. The pontoons in the enormous I-90 floating bridges are large enough to support a highway with over 50 million cars a year, and a new railway, the first of its kind on the planet. Tasked with maintaining the bridge, engineer Jim Stonecipher is heading out to take a closer look.
So our solution to crossing Lake Washington was building these pontoon bridges. We make a concrete pontoon out of very dense concrete with hollow cavities inside. The concrete has enough buoyancy in it to support the bridge and the traffic on it.
During construction, 38 giant pontoons are positioned end to end, giving the illusion of one colossal bridge base. Each pontoon is divided into cells and sealed with watertight hatches. 2 overhanging bridge decks provide enough space for 8 lanes of traffic and 2 train tracks.
One of the reasons we have so many pontoons is for redundancy, so that if one fails, it won't sink the whole bridge. Each compartment has its own door and sealed off, kind of like a ship. And that way, we don't lose a pontoon bridge and we can maintain traffic.
Keeping these mega bridges afloat is an impressive feat. But with no fixed footing, it takes more remarkable engineering to stop them floating away.
Down below us, you're going to see the anchor cables that help stabilize the bridge and keep them in place. And here comes one now. You can see them just below the water. The longest anchor cable is about 739 feet in about 165 feet of water.
Buried in the lake bed, movements from the bridges put immense pressure on these anchor cables, causing them to fray.
Nope, I got a cable here.
So, to prevent catastrophe, a team of divers working at depths of up to 165 feet are currently replacing damaged components.
The anchor cables are very heavy, and it takes a real big team to get those anchor cables in place.
So far, 32 huge new cables have been installed. But seasonal change means that monitoring them is essential.
From summer to winter here on Lake Washington, as the lake raises and lowers, the anchor cables become slack or tight. And we don't want increased pressure on the bridge, or we do not want the cables to be slack.
A rupture in the cables could spell disaster for the bridge. So it's crucial that, as the lake's water levels change, the anchor cables are adjusted to the correct tension.
So now we're down inside of one of 18 pontoons. Watch your head, a little rough. We're walking in through the anchor cables in one of the segmented compartments of the pontoon. And this is the anchor cable on the pontoon. This particular anchor cable is 579 feet long.
To haul such an enormous cable in these tight spaces, you need a compact yet powerful piece of equipment.
So this is the jack that we use to actually make the adjustment. This is a 150-ton ram. We use this to either extend the cable out a little bit or bring the cable in to maintain a 65-ton average on the cable.
The jack pulls with phenomenal force, but all Jim has to do is press a button.
So you can see the travel of the cylinder right there. We're actually very slowly pulling the cable in. Over here in the other room, you can see we have this air cap between the jacking plate and the jacking head. And so we're actually pulling the cable into the pontoon. So now we've gained about an inch. So we're gonna put shims in here.
These steel plates will bear the load when the jack is released.
Right now, this time of year, we only have to move it probably an inch. In the spring and the fall, we'll move it about 6 inches.
Adjusting the 110 anchoring cables is vital for keeping the bridge in alignment and maintaining a safe road surface for more than 50 million vehicles every year.
So if we didn't have these anchor cables, eventually this bridge would float north or south depending on which way the wind's blowing. End up maybe in somebody's backyard, and that'd be a pretty big dock for them.
Across a combined bridge span of 4.8 kilometers, these 38 jumbo pontoons support a lifeline for millions. Without these incredible floating bridges, the city would be gridlocked. Construction of this groundbreaking project is underway.
To my right is the first set of tracks. There'll be 2 sets of tracks here when the construction is complete.
But the new tracks create a unique danger that engineer Craig Delala must overcome.
The rail system is powered by a 1500-volt DC system. The return path for that current is the rails here. Nowhere has anybody put a 1500-volt rail system on a floating bridge in the middle of a lake.
But water and electricity famously don't make a good mix. If electricity escapes the tracks, it could spell disaster for the bridge. Surprisingly, the danger isn't one of electrocution, but of corrosion.
So anytime you have a steel structure, the risk of rust or corrosion, which is the loss of metal, could impact the bridge. By introducing rail to the floating bridge, it further increases the risk of corrosion to the bridge and the bridge structure.
When that current discharges into the water, it can corrode crucial components at the exit point, threatening the integrity of the very bridge itself. For this world-first construction project, Craig's team needed to come up with entirely new methods to eliminate destructive stray current.
So you'll see here that there's multiple elements of isolation, including plastic pieces here between the track and the fastener. We also coat the bridge with a special dielectric material that is also a high insulator for electricity. And so with these elements, we are able to protect the bridge from any stray current ever making its way onto the bridge.
But with this mighty structure at stake, engineers aren't taking any risks.
To move these barriers out of the way.
Should any stray current make it through the first line of defense,
This is going to be harder.
there's a backup plan.
The anode assembly is the one without a tape here. Okay. So what we have here is the anode coming out of the water. There's 8 of these that hang 50 feet down into the water. These are mixed metal oxide anode assemblies. These put current into the water, which is drawn into the bridge and allows the bridge to polarize.
Left unchecked, stray current could enter the lake through bridge metal. But over 1,400 anodes feed another electrical charge into the water. This protective flow drives into the bridge structure and holds the stray current at bay, saving crucial components.
Without corrosion control, the life expectancy of the bridge could be shortened. Applying it to a floating bridge like this is really something extraordinary.
The danger of corrosion has been eliminated. But as rail installation advances, an entirely new threat looms over the project.
So right now we're about to go across the bridge.
Keeping the mission on track is engineer John Slavin.
As we transition to a floating bridge, we are on a floating structure. And just like any marine vessel, it tends to move a little. Now for an automobile with rubber tires, they can go across an angle point or a bump quite easily. And this is very difficult for a train because steel rails need to be continuous. They can't have break points or angle points that could potentially disrail a train.
The floating bridge needs to contend with a range of movement caused by lake levels, wind, and uneven traffic loading. This stretching and twisting at the joints constantly changes the transition angle, threatening a track misalignment between lake and land. For 800 passengers on a speeding train close to heavy traffic and deep water, this could be fatal.
We need to find a solution across that expansion joint that's critical to the operation of the rail.
To evade a devastating derailment, John's team must connect with innovators of the past. Norway, famed for its vast fjords. Civil engineer Bertha Dongmo Angeland is on the hunt for a relic from the golden age of locomotive travel.
In the beginning of the 20th century, the quickest and most efficient way for factories to export their goods was by train. The only problem is to get access to the railway line. Those factories are located on the wrong side of the lake, and train doesn't float.
Scottish engineer Thomas Bush encountered a similar problem when extending Great Britain's railway lines. But in 1849, he came up with a solution that would roll out across the continent. The railway ferry.
Wow, look at that. This is so amazing.
Bush's concept of a ship with inset rails enables locomotive wagons to float across water.
This ferry here in Norway follows closely Bush's design. When railway ferry came here in 1909, it was a wonderful opportunity for the factories to export their goods by rail, and we are lucky enough to see it today.
But the ferry itself is only part of the story. Once the wagons have reached the end of the line on land, there's still the problem of getting them onto the barge.
This is the most delicate part of the operation. It's very important that the boat and the pier are at the same level.
A misalignment of the track would be catastrophic. And with lake water levels constantly changing, Bush needed a clever solution.
I have my miniature lake here, and the water level is low. And we have a gap here that can cause some problems for our train. So basically, we need to find a way to connect those two tracks together. The solution to this problem here is to use a hinge ramp that can move and allows us to establish a connection between the dry land and the floating barge And our train can now smoothly transition from dry land to the floating part. And the most important part here is that the hinge allows us to change the angle so that we can accommodate any water level. It's simple, but brilliant.
The adaptability of Boucher's hinged ramp is a concept that will prove instrumental for the team in Seattle.
So we are going to bring the ramp down and connect it to the ferry now.
With the help of an enormous winch system, the span is lowered and tracks perfectly aligned.
This transition ramp, starting exactly here, is hinged on one side, so that we can lower it or raise it, so we can always have this perfect alignment with the ferry.
Connecting these tracks provided a lifeline for the region's industry, with an astonishing roll-on, roll-off solution.
It's impressive. It's really cool to see this.
The remarkable railway ferry and hinged ramp configuration kept cargo wagons on the move and changed European locomotive transportation forever.
This innovative concept was a game changer. Train doesn't float, but vast lakes and fjords like this one were no longer an obstacle. And it's quite amazing to see that design still in action 100 years later.
A 170 years after Boucher's inspired idea, Seattle's greatest engineering minds have developed a system that he could have only dreamed of.
And so this is our solution. We call this a track bridge because we're bridging over that expansion joint. And it's an amazing, actually, solution that we came up with.
This unique design has to deal with conditions not seen on any other railway bridge in the world.
We had looked at some other systems, but this has 2 more degrees of motion that don't exist on other bridges. What we have is a system to try to handle all those different levels of movement, but rather than happening in one point on the rail, we've spread that over a longer distance. And how have we done that? Through a lot of components. As we go underneath here, we can see some different elements. Each of these wings have a curve to them. That means when the bridge goes down, because the lake level goes down, these wings will rotate up. And when the opposite happens, these wings rotate down.
These curved wings work in unison with a complex range of components to bend the rails into a gentle arc and keep them level over the moving angle points. 8 of these 13-meter-long track bridges will cross the 4 hinges between fixed and floating segments, allowing a smooth transition for the trains. After the complex track bridges are assembled, the system has to undergo extreme scrutiny to ensure safety, speed, and efficiency. So they're thoroughly tested at a special facility in Colorado, producing 500 channels of data.
Our test revealed that at our design speed, our maximum speed of 55 miles an hour, the track bridges were good, the stresses in the rails were fine, and the ride for the passengers was comfortable. If we didn't have this track bridge, it probably would have been impossible to put trains across the bridge. At the very least, we would have had to stop the trains and almost just bounce across it. At its worst condition, that may have even caused the trains to derail at that low speed.
With this incredible world-first design, Seattle's engineers are one step closer to conquering the seemingly impossible.
This is a completely new and unique solution addressed just for this specific location. Nowhere else in the world are there any track bridges like this. We have thousands of daily commuters that rely on this, as well as sports fans and university students.
Engineer John Slavin is in charge of the project.
So when these trains are fully loaded, we'll have 4-car trains, and each car will weigh approximately 175,000 pounds. So when 2 trains are passing each other, essentially doubling the load, which is very heavy in one spot, that puts a lot of stress on the concrete.
A massive 4-carriage train at maximum capacity could weigh 350 tons. When 2 trains pass, that's as much as 700 tons bearing down on a short stretch of bridge. This crushing load can put enough stress on the concrete to cause catastrophic ruptures.
We've done a lot of structural analysis on these loads and realizing it takes a lot of stress into the bridge. And so to preserve the lifetime, we need to figure out how to strengthen the bridge.
So how do you reinforce the concrete to withstand the full force of hundreds of daily train crossings? It's a challenge that might be impossible without the innovators of the past. The city of Lourdes, southern France. An important holy site for Catholic pilgrims from around the world. Civil engineer Patrick Nagel is going underground in search of a structure with the capacity for a colossal congregation.
Wow.
This is the Basilica of Saint-Pieu-d'Y.
I'm completely awestruck by this building.
It really is impressive.
It's built beneath the city to protect views of the sacred site above ground.
What is striking about this magnificent building is a wide open space. No central columns, no supports. And we can see the structural form of the 29 arches running the length of the building. And this creates a usable space of over 10,000 square meters, which can accommodate 25,000 people.
But this subterranean structure seems to defy gravity.
The flatness of the arches is maybe something we wouldn't expect. A typical arch is much more like this. These are very flat arches. It is clear that something special here is happening from an engineering perspective.
Engineering enlightenment came from Eugene Freycinet. In 1928, he perfected a method of concrete strengthening using strands of steel cable under high tension. This technique, known as post-tensioning, provided support for concrete beams of unprecedented spans. But hidden within the concrete, it's not easy to see how this system works.
So here we have a simple model. We have a number of wooden blocks which represent a concrete beam resting on 2 supports. And you will see a string running through the beams, which is simply there to hold together the blocks. If I apply a load to the beam, you will see that it is put into bending, and you can see cracks opening up within the concrete. So the secret is to put in compression before the load is applied.
To achieve the compression needed, post-tensioning must be introduced into the beam.
So in this case, it is provided by string and a tourniquet to tension the string. So I have now tightened up the stressing, if you like, and we put this back on the supports. So this time we can apply double the load, and we can see that there is no movement and the beam does not go into bending. This gives a much more efficient use of the concrete and allows us to provide bigger spans and more efficient use of the material.
By compressing the beam, its density and strength is increased, a method that could prove vital for Seattle's bridge engineers.
So essentially what we are doing in the beams, in the arches behind me here, is applying an external force to increase the load-bearing capacity of the structure. The tendons that we see in here are formed of steel strands housed within ducts and stressed by hydraulic jacks after the concrete is hardened.
The strengthened concrete provides a vast ceiling without the need for obstructive pillars. Instead, arches span the chamber and descend to the floor close to the edge.
Looking at the structure today, there are no cracks. It is very finely designed to make sure we maximize the capacity of the concrete.
The long, shallow vault of this hall would not have been possible without Freycinet's miraculous post-tensioning solution.
Today, we see it used in all major structures, bridges, buildings, dams, and without it, we would not be able to achieve some of the beautiful and brilliant structures we see around us today.
At Seattle's floating bridges, engineers are applying Freycinet's groundbreaking technique on a world-beating scale. Just like at the Basilica, they're fortifying concrete through extreme compression.
So what we've done to strengthen the bridge is put post-tensioning cables in the bridge.
But the supersized system on Lake Washington is using some of the longest post-tensioning cables the world has ever seen.
So these cables are approximately 4,000 feet long, running from one end to the other, one continuous cable in each one of these conduits. Very unique in this situation that we've added 4,000 feet of post-tensioning. Most post-tensioning is much shorter, 100 to maybe 200 feet.
With a combined length of 24,000 meters, 20 of these steel supercables are thread through the pontoons, spanning the North Bridge's floating platform. Powerful hydraulic jacks then pull them tight with immense force.
So what we've done is we've put conduits through the bridge. Those conduits are then used to string the cables through that, and when we pull those cables tight.
But keeping a post-tensioned monster cable in place requires oversized anchors.
So here are the reaction frames inside the bridge. These are the big steel frames that we pull tight against when we tension the post-tensioning cables. So their job is to hold the post-tensioning cables tight so that we put that force into the bridge to strengthen it.
20 massive reaction frames weighing 7.5 tons each are pulled inwards by the tensioned cables. Like huge bookends, they squeeze the bridge from either side. Compressing the concrete increases its density and so strengthens the bridge to take an even mightier load. Applying extreme compression to the structure has to be executed with pinpoint precision, to within 1.5 millimeters.
These frames are critical. Without them, there's no way we could have added post-tensioning.
The result is a super strong floating platform capable of withstanding the 700-ton point load of 2 trains crossing simultaneously.
So this is an incredible solution to the problem. Extremely long post-tensioning cables added to a bridge, allowing us to add the trains to the surface of this bridge.
For the team behind this daring project, the engineering achievement is immeasurable.
The floating bridge is an amazing structure. It's critical to our region.
This is one of the most challenging projects I've ever been involved with. Because of all the unique items, you can't just go take something out of a design handbook. You have to think about how each one individually interacts with each other to make the system as a whole perform well.
This has been a great project, and I can't wait to see it start in service.
The unparalleled twin bridges that have defied the impossible, spanning a previously impassable lake, creating a lifeline for a population of millions. And their brand new crowning glory, stretching thousands of meters from shore to shore. all stand as testament to the incredible work of some of Seattle's greatest engineering minds. The I-90 floating bridges represent impossible engineering on a staggering scale. Every stage of this groundbreaking enterprise poses extraordinary challenges.
There are many facets and many people involved in this design, and it's been really great working on this. I'm really proud to see it coming together.
By building on the work of the pioneers of the past, overcoming huge challenges, and pushing the boundaries of innovation.
This is some of the most incredible engineering that I've ever seen.
It's extremely exciting for me and my team to be able to work on such not only an important project, but a unique project.
The engineers are succeeding in making the impossible possible.